In what manner does the theoretical capability of this highly crystalline Fe-Pb material to undergo two Na-ion redox reactions translate into an experimental specific capacity of 170 mA Hg superscript 1? And how might this dual redox mechanism be fundamentally linked to the optimized crystal structure? How do the observed excellent rate performance and the achievement of 100% coulombic efficiency reflect on the efficiency of ion transport and charge transfer kinetics within the ordered lattice? And what does this reveal about the interplay between crystallinity and overall battery performance? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How can the noted good cycle stability and the absence of obvious capacity attenuation as shown in figure 3.49 be connected to the material's high structural regularity? And what mechanisms might be responsible for mitigating the degradation processes typically seen in less crystalline or defect-rich materials? How do these findings collectively enhance our understanding of the relationship between synthesis, structural control, and electrochemical behavior in Prussian blue analog cathodes? And what further experimental investigations or advanced characterization techniques might be necessary to explore any remaining challenges in translating these laboratory-scale improvements into commercially viable sodium-ion battery applications? How does having an extremely low vacancy content of 6% influence the crystal lattice in such a way that it brings Na-ions closer to the redox active sites? And in what manner does a low water content of 15.7% further contribute to this proximity of Na-ions to these active centers? How does this closer positioning of Na-ions facilitate the electrochemical activation of iron ions within the Pb lattice? And what role does it play in enhancing electron transfer during redox reactions? Given that these structural features are ideal for promoting efficient redox chemistry, how do we reconcile this with the fact that the Na.6 Fe-Pb material inherently exists in a sodium pore state, containing only 0.6 Na atoms per unit molecule? In what ways does this sodium deficiency compromise the material's practical applicability, particularly in terms of its ability to support the necessary ion intercalation and maintain long-term electrochemical performance? How might the imbalance between the advantageous positioning of Na-ions near active sites and the overall insufficient sodium content affect the reversible capacity and conductivity of the material? And what challenges does this present for its use in advanced battery applications? What strategies could be explored to overcome this limitation while preserving the benefits of a low vacancy and water content? And how might future synthesis or material design approaches be optimized to achieve a more favorable balance between structural perfection and adequate sodium inventory?